This is a multi-part series where I'm going to take you through a brief introduction to redox reactions and a little bit of electrochemistry and then some electrochemical calculations. So we're going to start with two different scenarios here. We've got this reaction one where I've got a solid piece of zinc is placed into an aqueous solution of silver nitrate compared to placing a solid piece of silver into a solution of zinc nitrate. Now, one of these reactions is spontaneous and one of these does not. Now, we're going to get into mathematical ways that we know that these are spontaneous, but for now, our primary focus is going to be your knowledge of activity series. You know, which metal here is more reactive. And the answer to that is part of the reason why silver is a precious metal is it's not very reactive. So silver's low on the metal reactivity series, meaning it stays as a metal more so than what zinc does. So this bottom, under normal conditions, this is not spontaneous. So we would say, this bottom one does not react. On the other hand, this top one does. Zinc displaces the silver away, so zinc will form zinc nitrate and solid silver. So what we end up with is this aqueous solution of zinc nitrate and solid silver. Now, of course, that's not balanced. If we look from left to right, zinc 1 and 1, silver 1 and 1, but 3 nitrates and 2 nitrates. So I need a 2 there. And then lastly, I need a 2 over here in order to balance it. So this is my spontaneous reaction. I'm going to use that spontaneous reaction for several of the things that we do in this particular video. And I'll talk about things that we know about that reaction. And again, try to give you some information how you could apply this to other single displacement style redox reaction. So what does this reaction look like? So I'm going to represent this reaction. So here is my zinc, and then these are the silver nitrates, and so the zinc displaces that away. So there's a zinc with 1 nitrate, silver alone, and now we get the second silver alone, and we get the ZnNO3 in parentheses 2. Now, in reality, if we go back and we take a look at this, because we talked about solutions, this is my solid zinc. These down below are the silver ions here in this solution, and these are the nitrate ions. And what happens is the zinc goes into solution to form Zn++ cation, and the two silvers become silver with a charge of 0, solid silver. And we'll represent that more so here in just a moment. Notice those nitrates, they didn't do anything. So we're going to talk about those when we do the net ionic here in just a few minutes. They're spectator ions. They're unchanged as we go through this reaction. So we know that the zinc displaces the silver from something called the metal reactivity series. And so the following, this is a list of the metal reactivity series, and we can see the more reactive metals, things like lithium, sodium, down to some things kind of around the middle, zinc and aluminum. A little bit lower we find copper, and then down toward the bottom we find those precious metals, silver, platinum, and gold. Those are the least reactive metals in the activity series. Well, redox is actually an abbreviation for two words, and they are reduction and oxidation. And oxidation is defined as loss of electrons, and reduction is gain of electrons. And one way to remember those definitions is by oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. But again, when we see that word reduction, but yet we talk about gain, sometimes that's a little bit confusing, but we're gaining negatives. So therefore, the oxidation number, when we gain negatives, it's going to decrease. So that's why it's called reduction. On the other hand, when we lose electrons, we're going to see an increase in that value. So if I go to that reaction that we worked with a moment ago, we've got zinc added to 2AgNO3 aqueous, forming Zn parenthesis NO3 subscript 2 aqueous plus 2 solid silver. Alright, so that's the balanced equation for this, but we're going to go through and we're going to do something called a net ionic. To do a net ionic equation, you need to know your solubility rules. I'm not going to go through those on this particular video, but you break apart anything that's in solution, anything that's aqueous. So we've got zinc plus, and I'm going to go ahead and carry the coefficient through in this problem, 2 silver plus 1 aqueous plus 2 NO3 minus aqueous, arrow, Zn plus plus. We're kind of undoing what we do when we put these together to make these ionic compounds, plus 2 NO3 minus aqueous, plus 2 Ag solids. So I've got zinc solid, aqueous silver ions, aqueous nitrate ions, zinc ions, nitrate ions, and solid silver. So that's a full ionic equation, but to do a net ionic equation, we're going to cancel what's called a spectator ion, an ion that's unchanged from one side to the other. And in this case, that's going to be the nitrate. Now the zinc, it changes because the zinc is not the same on both sides. The silver changes. So my final net ionic equation looks like this. Zn plus 2 Ag plus aqueous, arrow, Zn plus plus aqueous plus 2 Ag. So what happens if we have this same equation but it's not balanced? Now again, you can always put the spectator ions back in and you can balance it that way, but I want to show you how to balance this by the half reaction method because that kind of leads us into the electrochemistry part that we'll see here in a moment. So to do this by the half reaction method, to do the balancing, we write two half reactions, zinc forming the zinc ion and silver ion forming solid silver. So the first thing you're going to do, just kind of running you through the steps here, is you're going to balance the unbalanced elements, which they are currently balanced. If we look up top, the reason why this is not balanced, just to clarify, is you got one zinc and one zinc on each side, and one silver and one silver, but your charges from side to side, you got no charge on the solid, so you got a +1 total on the reactant side, but you got a +2 total on the product side. So that's why this is unbalanced. The charges aren't balanced in this particular reaction. So that's what we're going to do down below. Zinc 1 and 1, so we're good, but now we're going to balance the charges by adding an appropriate number of electrons. In the bottom one, you're going to bring the high charge down to the low by adding an electron. Notice you add it to the opposite side there to take that silver +1 down to silver solid with no charge. On the other hand, zinc, no charge, is zinc ion, 2 charge, plus 2 electrons. So here's where we get into a little bit of that definition. Oxidation is loss of electrons. So here we see that this zinc is producing electrons. On the other hand, reduction is gain. The silver ion is gaining that electron to be reduced. Now again, we can look back up top here in order to see this, and we still see this going on because we see that the oxidation number here goes from 0 to +2, so it increases, and the one that's normally much easier, charge goes down, +1 to 0, that's reduction. And most students find it easier to identify reduction first, and if you can get reduction, you can find the oxidation. So, picking back up with these two half reactions, now they're not balanced. We have to have the same number of electrons produced that we have consumed. So to do that, we're going to double everything in this second reaction. And now if we add these two half reactions back up, the two electrons, they're going to cancel out. Later on in electrochemistry, those two electrons will be part of some calculations that we'll be doing. So my balancing is 1, 2, 1, and 2. Same thing we get when we leave the spectator ions in, just another way to do it, but here we're actually showing production of electrons and then consumption of those electrons. This content, this part of the video, this next reaction I'm going to work with may be beyond first year chemistry. It's geared a little more towards second level chemistry, but it shows up when we get into more advanced electrochemistry. So I'm going to go ahead and go over this here as well. This is a redox reaction as well, but it's called an acid redox. And I know it's an acid redox because we see the H plus and the H2O. And that's one key that gives me that this is an acid redox. Now we could leave those out and they could simply just tell us that this occurs under acidic conditions, which gives us the right to go ahead and add in the H plus and the H2O as necessary to balance this equation. This is a little more advanced balancing by the half reaction method, but I'm going to go ahead and run through it here as well. So we're going to write our two half reactions, Cr2O7-, the dichromate ion going to the chromium 3 ion, and then ethanol, C2H5OH, forming CO2. And this is actually for an ethanol analysis. You can actually use this to check to see if alcohol is present. Use an acidified solution of, for instance, potassium dichromate, and we'll get a color change there, and you can measure the absorbance of that and actually use Beer's law and actually determine the relative amounts of ethanol present. So we're going to write those two half reactions. Now again, if you look at this and you kind of understand a little bit about dichromate, chromium in dichromate has an oxidation value of 6, so it's going from a 6 down to a 3. But the good news is you don't even have to pick that out. If you follow these directions for balancing acid or base redox equations, that'll actually come out in the end. You don't even have to look at that and say, oh, I can tell the chromium is going from 6 in dichromate to 3, so that's being reduced. Again, you don't have to do that. The directions say balance everything other than hydrogen and oxygen. So in this first one, I got to put a 2 there to balance everything other than hydrogen and oxygen. Second one, I'm going to put a 2 there to balance the carbons, everything except hydrogen and oxygen. The next step is you're going to balance your oxygens by adding water. So here we're going to add 7 H2Os to balance the oxygens. And then in this one we've got 1 oxygen, and over here we have 4 oxygen, so we need 3 H2Os added to that side. So step 1, balance everything except hydrogen and oxygen. Step 2, balance the oxygens by adding in the water. Step 3, balance the hydrogens by adding in H plus ions. So I've got 14 H plus ions. And then down here, I've got hydrogen present a couple of places here. I got 6 hydrogens and 6 more hydrogens for a total of 12 plus 12 H plus ions there on the product side. So step 1, balance everything except hydrogen and oxygen. Step 2, oxygens by adding water. Step 3, hydrogens by adding in H plus ions. Now we get it to this point, and now we're ready to balance the electrons. So to balance electrons, we need to total up some values here. I got a 14 positive and a 2 negative, so I'm going to jot that down. That's a positive 12. And then on this side over here, I've got positive 6. And I need to add enough electrons to bring the big down to the little. So that's going to be adding 6 electrons over here. Now a moment ago I talked about this changing from a 6 charge to a 3 charge, which is a change of 3. But if 2 of them do it, that's where the 6 electrons came from. But you don't have to identify that. If you just follow the steps, it'll still all work out in the end. On this second one, no charge, so 0 and 0. And 0 here, but positive 12 there is positive 12. Bring the big down to the little. So I'm going to jump over here and I'm going to add 12 electrons. Now it's real similar to what we did before. We've got to multiply to cancel out those electrons. So I'm going to double everything in this top reaction. So I'm going to get 28, 2, 12, 4, and 14. And now we're ready to add everything up. But when we add up, we got to look at a few different things. 1, did we cancel the electrons? Check. 2, I see 28 H plus ions, but I see 12 produced, so that's actually only a net of 16 H plus ions. So now those are done. Check. Check. And same thing with the water. I got 14, but I had 3 going in, 3 total on this side, 14 on the product side, so that's a net of 11. So cancel that now and cancel that. And now we're ready to get the other coefficients. So 2 with the dichromate, 1 with the ethanol, 4 with the chromium 3 ion, and 2 with the CO2.